All right, welcome everyone to this week's Autonomy Talk. We are kicking off 2024 with a new lineup of great speakers, the first of which is Bryce Ferguson from University of California, Santa Barbara. There is a PhD candidate in the Electrical and Computer Engineering department, working with Jason Marden. Something about Bryce. Bryce received his Bachelor of Science and Master of Science in Electrical Engineering from UCSB, and is already quite known in the field of multi-agent systems. He has won some awards recently, and in general, his research focuses on game-theoretic methods for describing and controlling social and engineered multi-agent systems. This is precisely the topic of today's talk, which is titled Information as Control, Emerging Paradigms for Multi-Agent Systems. This aligns very well with some of the works we promote here at Autonomy Talks, and I'm very excited to hear more about it. And I give you the stage, Bryce.
Okay, yeah, thank you for the kind introduction. So today I'll be talking about my work, like you all said, about the role information plays and how we can control multi-agent systems. And I'll be bringing in some ideas from game theory and that sort of approach. So, get my next slide going, hopefully. There we go. So I want to start off with an anecdote about the Grand Banks fishing fiasco, which is an area of the Atlantic Ocean off of Newfoundland, Canada, where there were very large populations of codfish in the mid-1960s. Now, naturally, this large population of fish attracted many fishermen and many fishing operations to come set up shop in the area. And understandably, the objective of each of those operations was to try to catch as many fish as possible. So what this caused was a large spike in the late 1960s of many fish being caught, brought into the area. But very quickly, the local population of fish was decimated, and by the early 1970s, the overall haul went from over 800,000 tons to below 30,000 tons. So you may be asking, okay, why is this guy starting off his talking about fish? Well, because it highlights this important example in multi-agent systems that local decision-making can lead to suboptimal global behavior. So here, each fishing boat making the local decision of catching as many fish as possible led to this suboptimal global behavior of all the fish population being decimated and there being none left for anyone to catch. And this is an idea of the tragedy of the commons. But we can see this phenomenon showing up in a variety of settings. So in like transportation problems, we have drivers choosing routes through the cities. When we allow drivers to make decisions in their own self-interest about which routes they take, it can cause congestion for other drivers. And we may think that new technologies being introduced will immediately help, but we've seen examples of things like Google and Apple Maps or Uber technologies actually worsening traffic in many cities or on certain roads. So this brings in this idea that, okay, the underlying phenomenon is the same, that local driving decisions lead to now here suboptimal traffic. And similarly, we can think of this outside of these social self-interested decision-making systems, where if we have this engineered multi-agent system where we have maybe here this fleet of ocean mapping drones, then if we design some local control algorithm for each robot, then we may get worse performance than if we'd have done it in the centralized sense, right? But the centralized approach may be have higher communication costs. We may not be able to attain that level of coordination, so we may need to live somewhere between the two. And then there's this a variety of emerging settings where agents or where we have this influx of new teams of robots interacting with one another, that we need to think about what the collective behavior of these interactions are. And here we see that by designing local algorithms, we may get just suboptimal behavior of the fleet. And then finally, we can think about settings that exist at the intersection of the previous two, where you have engineered and social components interacting with one another, like smart power grids, where we have interconnected suppliers and users of electricity, where certain spikes in demand or usage at different times of day for users at homes or offices can lead to reliance on more quickly generative power sources like fossil fuels and things like that. So there are new technologies such as, these like prosumer ideas and electric vehicles start to bring in new challenges as well. And what we see is that deciding supply and demand locally can lead to these large surges in suboptimal energy uses. So these three examples are all to say that we have this underlying phenomenon that we want to understand, local decision-making leading to suboptimal global behavior. And the central goal of my work is trying to develop new system paradigms and admissible control techniques to try to coordinate the interactions of these decision makers in these large scale types of systems. So particularly today, we'll focus on this goal and the role information plays in trying to accomplish it in three settings: the engineered systems that we mentioned, social systems, as well as the intersection of those two socio-technical systems. And each of these are going to be examples of multi-agent systems that we'll think about at a higher level. So I'll start off going into a little more detail on these engineered multi-agent systems, where we could think of large interconnected systems of many automated devices or processes, such as this fleet of ocean mapping drones like we discussed just previously, or in manufacturing robotics, where we may have many very similar robots trying to compete related tasks, but have to share those tasks appropriately, or the Internet of Things, where we now have these many connected autonomous processes. So when we think about what role information plays in influencing the behavior of these systems, we could think about how agents choose or are designed to share information between one another. If agents are making decisions locally, then the information they can be given from their fellow agents can dictate what behavior they make and then what behavior emerges collectively. So here we can think about the level of information that's shared between the agents can dictate some level of coordination between the fully distributed case where agents share no information with one another, and the fully centralized case where agents fully coordinate their behavior and are sharing information fully, maybe with some central source. So today we're going to try to understand the space in between the two of paradigms that are partially collaborative or partially between distributed and centralized. All right, so that'll be the first section of this talk, the interconnected collaboration ideas. So here I'll give an example. We can think about this sort of task completing robots, where we can think of two approaches of controlling them. Like I mentioned, first, a centralized approach, where we know we'll have good performance by using existing control techniques that exist. But the communication requirements may be unattainable of having each robot in real time communicate with some central source and have control signals sent back out. And on the other side, if we think about the distributed approach, we know the communication costs are going to be much less, but the performance can be poor. And to see why that performance is poor, I can give you this very high-level example where we just have these 6 orange task-completing robots and this set of red tasks. And if we set each of these robots not to coordinate together in any way, we can just send them out and say, okay, go complete whatever the highest priority task is at this time that hasn't yet been completed. And then what we see is that all the agents start essentially clumping together, each trying to complete the same task because they're unable to coordinate between each other which task they could maybe share or distribute amongst themselves. And we're not really getting full advantage of the fact the system is multi-agent, that we have these agents that could be working together. So here what we can say is, well, let's try to go beyond this and start to think of paradigms between centralized and distributed and understand what our performance is there, using this idea of coordination through collaboration, where we'll let agents form these collaborative decision-making groups that can hopefully give us better coordination than what we just saw in that simple example. So I'll go into a little more formal model here. We'll say we have a multi-agent system, which is just a set of n agents, a finite set of agents, where each agent has some local state or action, where AI is going to be the local action or state of agent I within some action set. And then what we care about is the collective behavior of this system, which is the tuple of each of their individual actions. And now each agent is going to have some local objective function that they seek to optimize, which depends on the collective action of all the agents and maps to the real numbers. So we, as the system operator, we also care about what this collective behavior is. So we'll have our own separate system objective function W that also maps these joint actions or collective behavior to the real numbers. So now if we want to try to design this multi-agent system to have some quality behavior, one first approach would be to say, let's just come up with some local control algorithm, maybe some optimal control that minimizes this local objective or maximizes this local objective. And then we can say the system reaches an equilibrium when each agent is simultaneously maximizing their local objective function or optimizing their local objective function. And now what we can observe is that these primitives of this problem form a strategic form game. And this allows us to use tools from game theory to try to describe these equilibria and the interactions of agents as the interactions of players. And we realize that this equilibrium that we just described is exactly that of a Nash equilibrium. So we can start to talk through this game theoretic lens of the behavior of multi-agent systems. So there's a large body of work that lives in this area of distributed dynamics in games and multi-agent systems for reaching Nash equilibria, or in some generalizations therein. So we can think about distributed algorithms from the sort of algorithmic game theory community, or asynchronous control systems coming from controls, or even multi-agent learning, where agents may use different learning processes. And we have the same idea of local decision-making leading to this idea of a Nash equilibrium. But even with these approaches and being able to reach this type of state, we have two challenges that pop up. First, a Nash equilibrium need not be unique. We may have multiple of them. And second, if the system does settle at one of these Nash equilibrium, it may not be optimal. There may be better states we could have ended up at. So we need to understand how these two affect sort of our performance of the overall system. So there's two opportunities we can think about on trying to overcome these challenges. The first is what we call utility design, where we try to redesign the agent's local objectives in order to alter the set of equilibria to hopefully better align with our system objective, that W function from before. And there's been some body of work that I've worked in, and I've worked with Dario Pacignan, as I mentioned, who comes from your guys' ranks at ETH. But then there's also this second opportunity where if we consider utility design, we're still thinking about agents making decisions locally, which may be a little bit overkill in some systems today, where there could exist some partial coordination that agents could have between one another. So we're going to focus in a little more today on this idea of collaborative decision-making, where we allow agents to in some way coordinate their behavior and understand what new equilibria emerge and what the performance of those are. All right, so if we think about a multi-agent system now, and we need some sort of collaborative, potentially system architecture to govern the agent's behavior, then we know the distributed approach is one extreme, where we have no collaboration, and we design some algorithm for each local agent. And then the centralized decision-making approach is the other extreme, where we allow agents to form one large group, follow one centralized algorithm that determines all their behavior. But we know the communication complexity of this can be very high and maybe be unreliable. So today we'll talk about these ideas that exist in between, where you have these partially collaborative decision-making groups, where agents form these now subsets or coalitions of agents that form some group algorithm that determine their group's actions or their group behavior. All right, and here what we'll try to understand is how we can trade off both the ideally improvements to equilibrium performance, as well as what added complexity emerges. Here, by allowing multiple agents to form these coalitions, we've now increased the size of their action set and the complexity of them even making a decision, as well as the cost of them communicating between one another to form these decisions. So we'll try to understand both of these aspects and how they interact with one another. All right, so to give this idea of why collaboration is helpful, or why it's something we may want to consider in these systems, I'll give you an example where we just have some system level objective. We're coming at this from our perspective as an engineer, where we have our objective function W and three decision variables, A1, A2, and A3. And these are the local state of each of our agents, right? So agent one has some local state or action A1, A2 for agent two, and so on. And now here, if we want to try to decompose this problem into some distributed approach, distributed multi-agent system, then we can just say, well, let's let each agent just locally actuate over their own decision variable. So now agent one just maximizes over just their state, just their decision variable, and agent two does the same, and so does agent three. So what we've done is we formed a common interest game where W is our common interest objective, ours is the system designer, system operator. And now we've said, okay, the equilibria of this system are that of the Nash equilibria, where now no agent can deviate to increase the objective function W. So if we think about enumerating all the possible joint actions of the system, we let A1, A2, and A3 be the coordinate axes of this box. Then if I give you an element in this box, what I'm telling you is this is some state, and it has some welfare associated with it. So if I gave you a specific state that I told you was a Nash equilibrium, then what I'm telling you is that it's optimal over all of these unilateral deviations by no agent being able to change their individual decision to increase our common objective W, right? So we have this idea of local optimality over unilateral deviations. But this, as we can see just pictorially, doesn't give us a strong optimality guarantee over this entire space of actions. So we can instead consider what happens if we let two agents collaborate or work together. So here, if we let agents 1 and 2 now jointly maximize the system level objective over their paired actions, so now we're maximizing over A1 and A2 at the same time, then now we get that our equilibrium will be optimal over this two-dimensional subspace, or that we can consider all bilateral deviations. And if we let every pair of agents coordinate in this way, then we reach what's known as a two-strong Nash equilibrium, where we're optimal over all bilateral deviations. All right. And then we can take this a step further to this idea of K-strong Nash equilibria, where we let groups of agents up to size K coordinate their behavior. Here, because we have 3 agents, if we let K equals 3 equal, the number of agents, then we recover that our equilibrium should be optimal over the entire state space. I would have shown an example with 4 agents, but my 4D PowerPoint wasn't working today. So hopefully this illustrates the idea of these sort of collaborative sets. But what it does allow us to do is consider this variable K, our level of collaboration, if you will, as something we can tune between 1 and n, again, the number of players, to try to bridge the gap between centralized and distributed, and understand what different quality of equilibria look like in that setting. Okay. So again, we can think about the types of collaborations through some underlying hypergraph if we choose. So we can let H be some subset of the power set of the number of players, where we consider different groups able to collaborate with one another. One type of these structures could be a network, where agents are allowed to collaborate over edges. Another can be this sort of intersectional collaboration, where agents can form groups where they can collaborate with agents near to them or behind them in this string of cars. Or we can think about local communication and maybe communication constrained environments, where agents can only form these collaborative groups if they are able to come close to one another, right? But today I want to focus on this idea of K agents collaborating as one way to try to arrange this space between distributed and centralized. So we'll consider the collaborative structure where up to K agents can collaborate. The benefit of this is that the equilibria we know are going to be these K-strong Nash equilibria. And then there's 3 questions I want to try to answer. The first is trying to understand, how does increasing K benefit the efficiency of our equilibria? Second, how does it add additional communication and complexity costs? And then finally, can we design the system any differently to try to eke out any additional performance? All right. So before I click the next slide, Yul said sometimes people like to ask questions in the middle, so I'm happy to pause just briefly if anyone had any, but I can also go on and start to get into the results a little bit. All right. Well, then I'll take that as everyone's engaged and ready to hear some of these results. So if we start off trying to say, okay, well, how much collaboration provides us with, or how much does collaboration provide us with improvements to efficiency? Then we run into this problem where we need to understand how the multi-agent system behaves, what is the equilibria, and those can be hard to compute. So the first thing we'll do is we'll bring in this definition that a system objective W is going to be lambda mu K coalitionally smooth, where lambda and mu are 2 vectors in RK, where we satisfy this definition that the average group deviation from any action A to A prime, so any group gamma, can deviate from A to A prime, and then we need to lower bound this effect by a function of the system welfare in action A and the system welfare in action A prime multiplied by lambdas and mu's, right? So what's really important to take away, instead of understanding the intricacies of this inequality, is that for any W, there will exist some lambda and mu that satisfy this definition. We just need to find the right lambdas and mu's, right? And this is this sort of smoothness approach from game theory extended to this coalitional setting. And now in our first theorem, what we can show is that if we find the correct lambdas and mu's, then we get this guarantee on the ratio of our equilibrium welfare, or the welfare of any K-strong Nash equilibrium, divided by the welfare of the optimal attainable state. So we can think about this as some notion of efficiency that we'll call efficiency of K, where efficiency of K being very little means we're very inefficient. Our equilibrium has 0 efficiency relative to optimal, and 1 means we're fully efficient. Our equilibrium is providing the same performance as the optimal. And then finding these lambdas and mu's is essentially telling us what our efficiency of the system is. And now we want to try to shift our perspective to this new 2-parameter search over which lambdas and mu's we should find. And we basically turn this complicated multi-agent system equilibrium analysis into just this 2-parameter search. And that's what we'll now focus on. So we can ask ourselves, all right, well, we have this new problem. Is it any easier to solve than the original one? And the answer is that in a variety of settings, that yes, it is easier to solve. And one of those is this idea of resource allocation problems, where we have a finite set of agents N. They make use of a shared set of resources R, where each resource has its own value. So here V sub R1 is the value of resource 1. And then each agent has an action that they take from some constrained action set of some subset of resources. So they have to choose from some constrained set of subsets of resources. So we can think of this as modeling different types of problems, such as drone surveillance, where the agents are drones who make use of different areas of some area or location to survey, and their actions are which area that maybe they choose to cover at a certain time. We can think about it as this traffic routing problem that we discussed earlier, where agents maybe choose how to route themselves through a city based on which roads connect to them from their source to their destination. And then we could also think about cloud computing and internet routing, or these types of task completing problems where our agents are maybe computers that need to complete different tasks amongst themselves and distribute those tasks in some efficient way. So here, thinking again at the high level, we'll say our system welfare, our system level objective is just going to be the sum over all of the resources of the value of a resource times this local welfare function W, which captures the idea of having more agents. So this cardinality of A sub R is the number of agents using resource R. And the more we have of those, we may have this idea of diminishing returns. So it may not be twice as good to have 2 agents surveying the same area of land, but it may be better than 1 in some way. And we can use W as this sort of primitive of the problem to try to capture that. So in this area, finding the centralized or optimal solution to this problem is known to be NP hard, and a distributed equilibria is known to have suboptimal performance. So what we're going to try to do is understand these partially collaborative equilibria to understand this efficiency of K on how we can live in between them. So building off that first theorem that we showed, where we can say if we find these lambdas and mu's to get a bound on this efficiency of K, then our proposition 1.2 shows that we can find those lambdas and mu's as the solution to K different linear programs that are order of n cubed and the number of agents, if that is interesting to you. And then instead of going into details of this specific linear program, I can show you what it provides us. So if we consider a specific problem setting where we have the covering problem, so our local welfare function is just that we get the value of a resource if at least 1 agent is using it. There's no additional benefit to having multiple agents share that resource. Then here we can say, okay, 2 known results are the extremes. In the centralized setting, we know trivially that we'll have each agent, we'll recover the equilibrium is the central optimal, and we'll get an efficiency of 1. And in the decentralized setting, there's a known result from Gehring in the literature that the efficiency is 1/2. Gehring and others in different settings. So what we can use this result for is trying to bridge the gap between these 2 settings. And now we can use this linear programming approach to get these efficiency guarantees for levels of collaboration between fully decentralized and fully distributed. And we see that there's this smooth transition. So there are benefits to living in between the world of decentralized and the world of centralized. And this sort of motivates to start to think about when is it maybe effective to try to implement some of these techniques or some of these ideas of collaboration. All right, so now I want to transition into thinking about, all right, we saw that there was some benefit to adding collaboration to the system. What does it cost us, right? If we have agents working together, there's going to be some cost of them communicating and coordinating their behavior. So one way we can think about that is this idea of computational complexity of finding an equilibrium or even evaluating an equilibrium. So if we let n be the number of players, m be the number of actions a player can have, and k be the size of coalitions, then just evaluating a Nash equilibrium is just the number of players times the number of actions they can have. It's n times m. But when we form these larger k-strong coalitions, then we have both potentially a larger number of collaborative groups, and also those collaborative groups need to make decisions over a larger space. So instead of trying to go through each space and exhaustively determine which one is an equilibrium, which one is not, we can try to think of which dynamics lead us to these equilibriums. And there's a large variety we can consider. Some of that is future work. But one initial thought we could think of is just this idea of the K round robin dynamics, where we say we have groups of agents. We just order each possible group, all the n choose K groups in a line. And then we go through one by one and tell them to update their group action and try to see where this takes the system state. And what we see is that we can get a complexity bound on the number of best responses that need to be done, or I should say the number of welfare comparisons, to try to bring in the idea that larger groups have larger decisions. And we get that this is on the order of m to the n times this small order exponential. So we do have an increase in the number of welfare comparisons that we need to do from the fully decentralized setting, but it's somewhat small increase from what we could have done in this collaborative setting. But that's maybe not the most palatable, at least it wasn't to me. I'm saying, okay, well, it's going to take a long time. Maybe it doesn't take that much longer. It's still going to take a long time. So maybe we can think about, well, what does our performance look like before we reach an equilibrium? So before convergence. And now we can think of these K asynchronous best response dynamics. So we let the next group to update be a random variable. And we have this now random process of who updates next. We can think about each group having some internal Poisson clock of if they form a group and if they choose to update. And now if we let P sub zeta be the probability that a group of size zeta forms and performs the best response or an update to their joint action, then we can get this bound on our expected cumulative welfare up to time t that depends on how much we sample different group sizes. So as we select groups, larger groups with higher probability, then we'll get this better transient performance guarantee or in the meantime before we reach an equilibrium. And I think this highlights this idea well that choosing larger groups of agents to work together is going to give us better guarantees at the cost that we can understand well here. All right, so now I'm going to transition to this third point that I wanted to talk about. This idea of if we can design the system to maybe perform any better, if there's any additional performance we can eke out of it by redesigning how the agents behave. So up to this point, I've been considering this problem where we have a system objective W. We decompose that to each agent to form a common interest game where each agent has the same objective function, but they maximize over just their local or group decision variable. And when we did that, we saw some set of equilibria emerge. If we think about this distributed setting, then that was Nash equilibrium. And we can call that set Nash equilibrium of W, W being our objective function. And we noted that each of these was a local optimal of this function W. But now we could think about, well, what if we had the opportunity to redesign this objective function? So now we can choose this function U to be what the agents actually choose to update. And now we'll get some new set of equilibria that we can call this set of Nash equilibria of U, where U is our designed agent's objective. And now we'll say an equilibrium is going to be a local optimal of this new function U, but we'll still evaluate the performance of these equilibria with respect to our original objective W. So we still have the same objective in mind. We're just choosing what the agents decide to optimize. And now if we look through the set of equilibria and what their respective performances are, we may see that some do better and some do worse. But here in the setting where we designed U, just this example, we may get that the worst equilibrium gives us a better guarantee than the worst equilibrium in the other setting. So if we're trying to design to give good guarantees over the entire set of equilibria, then there may be some opportunities to design this function in that way and design how agents behave. All right, so now we're going to ask ourselves, well, how do we do this? Well, what is this problem? How do we design the agent's objective functions? And then can we do so in the collaborative setting as well, beyond just the distributed one that was sort of highlighted here? So I'll introduce the utility design problem where we want to design this utility function U to optimize over the worst case equilibrium performance. So here we're looking at the ratio of the worst case equilibrium over the set of now K strong Nash equilibrium when U is our agent's objective relative to the optimal. And we're measuring performance relative to our original objective. And here I'll also say this is going to be subject to some informational constraints. If we had large ability to compute this U, there may be some ways we can do so in a way to guarantee that the optimal is always in an equilibrium. But that may not be the only equilibrium, and it may also be the case that just finding the optimal, or it requires finding the optimal to do that, and that can be a challenging problem in itself. So here I can just say in words, the next sort of results is that we can, in these resource allocation problems from earlier, extend the linear programming approach to solve this utility design problem for the optimal utility design for K-strong Nash equilibria. And we can again see the effects of this, where if we look between the decentralized and the centralized setting, we can see significant improvements emerge when we now design how agents behave. So here, this red line is showing us our new efficiency guarantees when we were able to design this utility function U. And we observe these two key factors of these collaborative systems. The first is that we need to consider the level of collaboration and also how collaborative decisions are made. Here, we did that by a design approach, but we can consider other ways of how collaborations are formed and how collaborations are sought out or acted upon, you could say. All right, so these are sort of the three ideas of collaboration, and we can try to tie them back into that initial, just sort of high-level problem of this robot planning, where if we let agents start to work together in choosing which tasks they complete, we can see they distribute the tasks amongst themselves better than in this K=1 setting, the top left, where they all clump together. And certainly we get that as we increase the level of coordination between the agents, or they're able to form larger groups that are able to work together, we're going to get better performance. And we can ask ourselves, okay, is this increase in performance worth it as a function of the cost or the communication costs between the agents to attain it, if that makes sense. All right, so this was all tying into this first part of the talk on engineered multi-agent systems and how we could think about information as this mechanism to coordinate behavior between engineered autonomous agents. And we saw these three sort of interesting insights that, well, first, we were able to extend this game-theoretic approach to now collaborative settings where you have equilibrium beyond just distributed, but these sort of K-strong collaborative settings. And then we were able to use that to gain some understandings on the benefit and cost of collaboration, and new insights emerged on how we can design collaborative systems as well as, just distributed ones or just centralized ones. But now I want to shift gears a little further and think about not all multi-agent systems are engineered. Not always are the components these designed autonomous agents who we can tell to form collaborative groups and form these collaborative group interested updates. Instead, we could think about social multi-agent systems where we have the interconnection of many potentially self-interested human users, such as in the supply chain where we have many buyers and sellers of goods, or in mass transit, like I brought up in the beginning of the talk, where drivers select their own roads, or even in social networks where human users make decisions about information to share or how they interact with one another online. So here, if we want to think again at the high level what the role of information is in these systems, then we can think about this idea of strategic information revealing, where if we think about how a human user makes a decision, they have some underlying belief on the state of nature that leads to what action they take. So here, these drivers would have some belief on what the state of traffic is, and that leads to their action of which routes they take through a city. And then we have this opportunity, if we have some central source or some information source, like in the driving example, Google or Apple Maps, who has access to larger amounts of information, as well as the opportunity to reveal or message partial pieces of information to the drivers to update their beliefs, that they form new beliefs and now take new actions and just new collective behavior. And here we can think about, is this information revealing mechanism something we can exploit to try to get better performance out of the system? So this is going to go into the second part of the talk, this idea of strategic information revealing as a mechanism for trying to improve system performance in social systems. So here we'll tie back to this idea of a multi-agent system being a set of n agents now being human users. The agents now have individual choices, and the collective behavior is still captured by the tuple of each of their individual choices, so their collective choice. And then we can think about the individual preference, or the local objectives now being their individual preferences, so what each human wants to do, human user wants to do. And we as a system designer still have our same objective W, maybe not the same, but some setting relevant system objective that we care about maximizing. So now we can ask the system operator can ask, okay, well, what's best for me? Or what's best for the user, I should say. And each of them are going to make decisions in their own self-interest. So not in the setting of designing some distributed control law, but just thinking of humans as people who make decisions that are best for them in their self-interest. And now we can do the same thing of observing that these parameters form the primitives of a strategic form game. And we can again use tools from game theory to describe the interactions now of human users as players and see that the same type of equilibrium emerges, that of a Nash equilibrium, where now we can think of it as a state where no human user can deviate to increase their individual situation. And it's this sort of a selfish equilibrium that we reach. So there's a variety of settings where we can realize that self-interested behavior is not always optimal. We saw that in the engineered setting. It's certainly true in the social setting as well. So in traffic, we get congestion from drivers congesting the same roads. In supply chain, we see that when users have uncertainty on the availability of certain commodities, such as toilet paper over the COVID-19 pandemic, that can lead to a run on the supply, and maybe we have certain negative consequences there. And then we also saw this in the power demand sector where users all choosing to use electricity at the same time of day in the mornings or after work can lead to high demand and the need to rely on fossil fuels and other electricity sources. So if we want to think about trying to reduce this inefficiency or try to coordinate the behavior of selfish decision makers, two opportunities immediately come to mind. The first is the well-studied notion of monetary incentives, where you can design some sort of fee or reward system to try to alter the user's decision-making and try to get better performance for the system. And the second is to think of informational incentives like we just saw in that example with traffic, where we can reveal messages to users to try to change their beliefs as a now less direct method to try to change their behavior. And it's the second one I want to focus on a little more closely today. So to think just at a high level here of how this works, let's say we have a city where we have a user here who needs to route themselves through one of two roads, road A or road B. Road A is known to take 30 minutes, whereas road B is random. In expectation, it takes 40 minutes. So the rational driver will choose to take route A every time, essentially. But on a given day, it may not be the case that the actual route takes, or route B actually takes 40 minutes or more. It could be that on that day, the realization of the time to travel through route B was that it only took 20 minutes. And here, if we have some system observer or we have Google Maps who's able to track driver speed and collect this information, then they could choose to signal this information back to the human user who may then update their action and now choose to take what they see as the faster route. It only takes 20 minutes. But we also have opportunities beyond this where we could say the information source, Google Maps here, doesn't need to reveal exactly how long it took. They could say, oh, well, it's going to take between 0 and 35 minutes. In expectation now, it's only going to take 25 minutes. The rational driver will still choose route B, but sometimes they could be taking a route that actually took longer than route A. So between this 30 to 35 minute range, they're actually spending more time than they would have if they'd chosen route A. And we see this opportunity to influence the behavior beyond just what was selfish, essentially, and try to design these sort of information revealing mechanism where we can group different pieces of information to try to strategically shape the user's posterior beliefs. So then we can ask ourselves, okay, well, if the system operator doesn't just have one unknown, maybe there's a large network of roads with different traffic conditions and congestion rates that are all correlated with one another in different ways, then how should this system operator reveal information and what are the consequences of that? So I can go into a little more detail in the model here. So we'll say this, we focus on this in the setting of Bayesian congestion games, where we'll say we have a network flow problem where each edge in the network has a latency function that depends on some unknown state alpha, where we'll group this alpha into a vector where alpha ED is the scalar on some basis latency function L sub D that comes from some set of basis latency functions on edge E, right? So this exists in some large vector alpha that dictates what the performance of the, or what the congestion rates in the system are. And I will say that the users of the system have some prior belief. We'll say it's a correct prior belief in this work where they just think of what is the probability that different alphas emerge. And then we can think of a signaling policy as a mechanism that takes some realization of this alpha to maybe a distribution of signals that they could reveal about it. So say we had this cloud as our support of alpha, then we could think of a signaling mechanism as partitioning this space into here 4 signals, where if the realization of the state is within one of these regions, then we'll tell the agents that, so they know this realization exists in M3, and they can compute some posterior belief based on that. And the agents update their beliefs in that way. And we can also be slightly more general, where we could say, okay, even though the realization is in this M3 region, we could sometimes tell the agents M2 or M1 or M4, and the agents now have to use this Bayesian inference process to determine what the probability of different realizations are. All right, so try to illustrate what is sort of helpful and hurtful in the setting. The first thing I'll note is this lemma that says our total latency in an equilibrium for this problem, a Bayesian Nash flow, is equal to essentially the linear or the convex combination of the deterministic total latency in the expected posterior states, or with expected posterior alpha. So what does that mean? How do we use that? Well, if we consider an example here, where you just have 2 edges and 1 unknown, alpha 2, 0, we'll call it. Then what we can do is look for every value of alpha 2, 0, what the deterministic game's system cost would be. And then we can go through and say, okay, well, if we didn't have any information revealed, we have 1 expected prior alpha 2, 0. Then this lemma tells us that our system cost is, without revealing any information, is just equal to the point on this graph associated with this prior expected value. But if we chose to reveal information and we sent a message M1 when alpha 2, 0 is less than its expected value, and when alpha 2, 0 is greater than its expected value, then we would get 2 new posterior expected values. And this lemma tells us that our new system cost is just a convex combination of those 2 on this vertical strip. And what we see is that because this is, we see that the new expected cost is below the original one, and we get that revealing information lowered system cost, and we'll call this a positive benefit. So this B of pi here will be the benefit to revealing information. Okay, but now we can think of a separate example where we still have, we have 2 unknowns, but they're parameterized by a single variable, which leads to this new plot. And if we think about revealing information in the same way, following these new expected posterior system costs and doing the same convex combination, we see that we actually increase the system cost by revealing information, or the benefit was negative and signaling actually hurt our performance. Okay. So one thing to take away from this is this understanding that, okay, seeing this system cost, it should be intuitive that concavity is a good thing to observe and convexity is bad. That's something we don't want. We can think of these applications of Jensen's inequality to understand that, right? So now we can ask ourselves, okay, well, when do we want to use this mechanism? Is it effective? So if we think about information revealing mechanisms, our first sort of proposition here says that in Bayesian congestion games at large, there exist scenarios where revealing any information at all can worsen system performance. That's truthful information. Any information revealing can make system performance worse. And what this is representative of is that if we choose to reveal information in some unintelligent way, there may be settings where no matter what we do, it can be negative, or there implies that there are settings where the wrong information revealing can be negative, and maybe there existed ones that were positive. And this just highlights the idea that revealing information can have negative costs, and it's something we need to be cognizant of. So then we can turn our mind and say, oh, well, what if we just went back to that more traditional incentive, monetary incentives, and we try to institute these fees or subsidies. And then what we show is that in Bayesian congestion games, we still have examples where any monetary incentive, non-generic monetary incentive, can make system performance worse. And what we see is, okay, well, this may not always be effective as well. And what we can think about is, well, what happens if we use these 2 mechanisms together? Do we get any additional opportunities? And the answer is yes, that in Bayesian congestion games where we concurrently use information revealing mechanisms and monetary incentives, we can guarantee the system performance is only improved or not worsened, right? So we've essentially robustified this idea of revealing information by using the appropriate monetary incentives. And we see new opportunities that we didn't have with the respective ones, all right? So to highlight this just quickly with a sort of proof outline, so we can show here, say, okay, let's say we have two unknowns, alpha 1, alpha 2. We have some support of this random variable, random vector. Then what we're going to do is say, all right, let's draw a box around this. We'll call the box the bottom left corner of alpha down hat. And then what we'll do is look at the system cost at each realization of alpha in this box, and we'll get some surface. And now from that lemma before, we know that without signaling, our system cost is that point on the surface associated with the prior belief. And then if we want to think about what the possible consequences of revealing information are, we need to think about all the possible convex combinations of points on this surface, which we can capture by looking at the convex hull of the graph of this function, right? And then we can say, okay, well, our possible positive or negative change in system performance is equal to the gap between the surface and the hull, right? And we can use this largest possible gradient along this hull to bound that gap. So one result that we have is trying to use these geometric properties of the system cost function to get these bounds on the possible positive and negative benefit of revealing information. And now we can say, well, what happens if we concurrently use monetary incentives? Then we go through the same process. We take our two unknowns, we draw this box around it, and now we look at the total latency at each realization in the box while using monetary incentives. And we get this lemma that says that the system cost over this space is now concave when we use marginal cost tolls, okay? And what we see here is that now our convex hull is going to have no gap between the surface and the hull itself, right? Because it's concave. And we see there's no possible negative benefit from revealing information. So here we observe that the concurrent use of signals and tolls now ensures that there's no worsening of performance, the theorem 2.3 from earlier. And I won't go into the details, but we have some additional results that show that we can solve for the optimal signaling policies using ideas from generalized moment problems as well. So this highlights this idea of the interplay between pricing and information being an important one to think about. And as we see these new emerging transportation technologies, such as taxis and ride shares, where we have uncertainty about what the cost will be or about what the availability of Ubers will be or Lyfts. And then we can think about congestion pricing as something coming new into areas like New York, where certain regions are having new sort of tolling paradigms where information about not just what costs will be, but about what demand and congestion is going to look like can affect how drivers make decisions. And then even going into further into the future, thinking about these autonomous mobility services like autonomous shuttles or robo-taxis, where we need to think about how the vehicles make decisions about where to route themselves with uncertainty about demand and also what sort of prices they'll set, and really the interplay between the two. And this extends to settings outside of just transportation, of course, like the supply chain, where we have uncertainty about upcoming demand and supply and thinking about this bullwhip effect being mitigated by potentially information being shared and also what the effect on cost and price is, the price point of different products. And we can also think about it in this news media setting where having to pay for information can also be thought of as sort of the interplay between pricing and information. All right, so all of this sort of ties together under this idea of the strategic use of information in social multi-agent systems, where we saw that revealing information to human users needs to be done carefully unless we're able to concurrently use monetary incentives and informational incentives, which we get new opportunities, and it highlights this important interplay between information and pricing. All right, so now I'll just briefly touch on some additional opportunities in future work and then open up to some questions. But, my work largely focuses on this idea of developing tools and algorithms for large and complex systems. Here we focused a lot on some game-theoretic tools. But I also want to focus on some future directions that we can think about that I think are worth discussing, where instead of just focusing on these game-theoretic approaches, where a lot of the results are predicated on this idea of equilibrium, we can start to think about, and I tried to eke out some of those ideas with one of the results earlier, about the performance of the system in its transient. So if we have settings like this robot path planning problem or task completion problem, then the system objective may be changing very quickly, and we may not be able to rely on reaching equilibria and the performance of an equilibrium. Instead, we need to think about what our performance is as we converge to one. And much like we think about, tracking or an equilibrium being stable in a dynamical system, implying we may be able to track a reference, if we're able to get good convergence guarantees towards a Nash equilibrium in this distributed setting, then we may be able to get good performance guarantees as we track now an approximation of the system optimal through this sort of price of anarchy approach. And then we can also think decision making is not just made by best responses or other sorts of dynamics, but when we bring in ideas from learning, what does information look like in those settings if we don't want to rely on agents having large amounts of time to sample the entire space and have large visitation probabilities throughout the system? Then we can think about, well, how does the amount of information we collect lead to better or closeness to equilibrium and hopefully better performance as well? And then secondarily, if we think on these social multi-agent systems, then, the results I presented here and a lot of the work, in game theory and other settings have this reliance that human users are essentially rational, making decisions in their self-interest, which is a good first pass model. But human users don't always make decisions in their own self-interest. Instead, they have some finite and imperfect memory for past events that cause them to take some non-Bayesian potentially inference about the system state that may emerge. So here, an interesting idea that I want to pursue is thinking about how can we leverage this sort of transience and belief formation of humans, as well as this uncertainty, and try to manipulate in that way and try to guide the user's behavior in a dynamic setting, which there's some work emerging in, and I think is a very exciting area as well. And then, we can think about designing maybe robustly around this idea that we don't know exactly how human users are going to respond, but we need to think about it in this, like I said, more robust sense. All right, so with that, I will thank my collaborators that I've worked with, Jason Martin, Philip Brown, Dario Pacignan, one of your own, and Barry Prodelsky. I'll thank our funding sources, and then I'm happy to take any questions.
Thank you very much, Bryce, for the great talk. A lot of interesting topics. Let's open the stage for questions. You can either write in the chat and I can read for you, or you can just raise your hand and speak directly. Okay, maybe I'll be the icebreaker. I like both parts, but I had a question regarding the first one. So it's interesting how different levels of exchange of information can change the performance. Have you thought about the same idea in the context of multi-scale games or multi-stage games, where the exchange of information can happen between different stages, right? For instance, Stuckelberg games is an example.
Yeah, that's a good thought, and I think definitely something worth thinking about. I've thought a little bit about. I touched on there. Here I basically just defined an equilibrium notion or brought in one from economics and changed it a little bit to fit distributed optimization. So I think, honing in on two things. One being the sort of different structures. K-strong may not be the most relevant for different settings, but what sort of collaboration structure and what communication channels are there. And then thinking about the dynamics of collaboration. One thing I touched on was like, oh, well, what if they can only communicate while they're close to one another? Maybe the collaboration is action dependent. And then, thinking about it in this sequential setting could be interesting as well, for sure. I haven't thought too much about that, but I think, some of the, Stackelberg literature, thinks about information being passed along in that sort of strategic, making decisions, knowing things will be learned about you further on. That could be interesting to bring into the collaborative setting as well, like this.
Yeah. Okay, thank you. I saw there was a question from Alessandro, I think.
Hi, Bryce. Thank you very much. I'm Alessandro from ETH. I had a question about the first part. So when you were talking about coalitionalism of games, I understand that this is somehow kind of you use it in a descriptive way to model the properties of having larger or smaller coalitions.
Yeah.
But I was wondering if you actually also use or can use it for, let's say, for planning, let's say for solving the problem. Because at least in my experience, usually, even if you set up the game as a congestion game where you have robots competing for spatiotemporal resources and so on, once you start to model things like collisions, robots that need to avoid each other. Those games are not really smooth anymore. So I was wondering if that was to some extent just a pure descriptive characterization, or there was also some more practical parts that you can use for planning.
Yeah, that's a good question. So I haven't thought too much about, collision avoidance in particular affecting smoothness. Here, like I mentioned, if you can capture really any problem in this sort of setting as some system level objective in a common interest game, then there exists some lambdas and mews. So maybe through the right lens, you could say, oh, if I make the action sets or the behavior more complicated, maybe that changes what my smoothness variables are. Sort of the traditional approach from congestion games is saying, I have this game, I want to find lambda and mews to try to understand what the performance is. Here we're saying, oh, well, we can design the game a little bit and we can come up with some search for lambdas and mews based on what game we're considering. So potentially that's something our tools would be a little bit more amenable to, maybe not designing the system, but being able to find lambdas and mews for how you design the system. I think that could fit in. But I haven't thought much about the collision avoidance, so that's interesting to think about.
Okay, thank you very much.
Yeah.
So there is a question in the chat. I'm not sure I read it correctly, but it says, can you please maybe redefine what the notion of equilibrium in a multi-agent system is? I think you touched upon many different equilibria notions, right? So, but maybe a synthetic answer for Zoran could be.
I guess the starting point for both of these sides was a Nash equilibrium, I guess, was the equilibrium we were considering. And then just two generalizations along that. One was these ideas of strong Nash equilibria or K strong Nash equilibria, and the second was Bayesian Nash equilibrium. So yeah, multiple equilibrium concepts, but they all stem from that root of Nash equilibrium and unilateral deviations for agents.
Thank you, Bryce. So let's see, is there any other question from the audience? Okay, doesn't seem so. In case you have questions, I guess Bryce had his email somewhere. I saw it in some slide.
It was at the beginning. Oh, no.
Oh yeah. Oh, maybe not. Okay. Anyways, I think you can find I've seen everything is up to date online about you, so people should be able to find you. Thank you again very much, Bryce, for the great talk. Also, keep me posted on the next steps. I would be happy to hear more about the journey.
And when you're down in Santa Barbara, reach out.
Yeah, absolutely. And take care. Thank you, everyone, for joining. See you all next week. Bye-bye.
Thank you, everybody.